Let's move on to the next talk. Nanaz, talk about the star acquisition.
Thank you.
15 minutes.
Hi, my name is Nanaz Fathpour, and I'm part of PACE team, Pointing Acquisition and Control Management. We designed delivered algorithms for star acquisition, line of sight control, and that Milan Mandic is going to talk about, and focus and certainty controls that June is going to talk about. So I'm starting with acquisition, star acquisition. These are the team members that are not at JPL any longer. And we did a lot of testing of our algorithm. And I want to acknowledge the functional test bed folks. Okay, so I will talk about the different modes of star acquisition, XScan and raster scan. And then this is a system level kind of a task, star acquisition. So we will talk with the ROMAC ACS all the time during our acquisition. So I want to touch on the communication and exchanges between attitude control systems and CGI. And also I'm going to talk about the feedback results that we have. Okay, the XScan acquisition, this happens once per observation and at the very beginning of the when CGI starts doing its thing. So it happens when the optical path is unobscured. So focal plane mask is not inserted yet. So there's no dark hole yet at the beginning. So we have this interface requirement with the Goddard ACS team that they would bring the star within 4 arc seconds of our XCAM target pixel. So this is when that the other instrument on drone, field instrument and the fine guidance sensor has already been stable on the stars that bring the CGI star of interest into the camera's field of view. So our algorithms will, now that the star is on the field of view, the acquisition algorithm, which are implemented flight software, will find the star, its location, but we have one of the conditions for a successful XCAM star acquisition would be to bring the star, the PSF, to within a threshold, desired threshold, which is 54.5 milliarc seconds. So we need to go from 4 arc second to 54.5 milliarc second. And CGI does not have the pointing capability to do that. And this is very important because this is a system level. We are using the pointing capability of the attitude control systems. And during our time, developing these algorithms, it was very helpful to talk with the ACS system. We had the bi-weekly meetings for the past few years. So they exactly knew what the pointing needs that they want. And we communicated a lot. I think that's a very important lessons learned from successful star acquisition. So what we do is we communicate with the attitude control systems. We offload them the centroid relative to the desired pixel location that we want. And as 2 angles, we offload it to the spacecraft, and spacecraft will do the correction and bring the star to the desired. It does that over and over until it brings it to the desired region that we want. Know that the star is at that threshold region. Say that it is a successful XCAM star acquisition. And this is where I'm a little bit out of sync. This is where we are good to insert the focal plane mask. And we do the waveform flattening, phase retrieval, be able to take initial images and to complete the initial acquisition process. And eventually, we can close the line of sight view and start offloading the FSM strain gauge measurements to the ACS. Okay, so quickly talking about because this is coming, how do we talk to the ACS, the Roman ACS? So they would send us flags. The flags would be like the status of how the spacecraft is doing. So they would send us the flag and they would tell us that they have the required pointing capability that we want to start the CGI observations. On the other hand, we will send them the tracking state of the instrument, that if we are ready for the correction. So these two tracking states tells them that we need to give them some offloads for corrections. Whereas when we are in full latitude, they tell us that they have the required pointing stability and we can do the CGI observations. One of them is CGI acquisition. So when we are here, then we can do our star acquisition unless that we need to offload. So we go here and they do the corrections. They send us a flag that now we are at the required pointing that you can resume acquisition, and we go here and we do the acquisition. So this was a pretty complicated and complex piece of flight software, and we managed to test all of these. Of course, we don't have an ACS, attitude control system, a JPL during TBAC, but we had the GSCs, CBS. We used the CBS. We could prove to ourselves that software is doing what it's supposed to do. So we did, for XCAM acquisition, we actually placed, this is a 4 arc second radius that we have this interface right here. System to bring the star within this. We placed the star at different locations. We even put the star outside that 4 arc seconds, and from here we need to bring the star within the desired threshold region. So this is this little star here. Is this 2.5 pixels or 54.5 seconds, and we used the CBS to place the PSF at these locations, and then we did compute the centroid and offset from that desired pixel, gave it to CBS, and CBS did the correction for us. CBS was our ACS as well. And so we did it with the different type of stars, bright and dim, and all of them were successful. I show one of the examples that we have. We placed the star at 4.24 arc second, and we find the location of the star, and that we offloaded as delta H and delta V radius in a frame that we have defined and agreed with the attitude control system. And we offload that, and the next time around, when we do the acquisition, we see that we are at 1.147 arc second. We do another offload, this time much smaller, but we are not at the desired pixel location that we want. And this second offload brings the PSF to the desired location that we want. And that the flight software at this point gave us the success EDR that we have acquired the star XCAM. Okay. So we had a bunch of requirements, flight software requirements for this, and we ensured successfully that we can meet all those requirements. Okay, the second method that we have is a raster scan star acquisition. This comes a little bit later. This is after dark hole digging. So the focal plane mask has been inserted in the optical path. The field of view is now obscured. So we needed to do something else. We needed to have another method in order to acquire a star. So what we do here is, first of all, this happens during blue and rose when we acquire and reacquire stars. And we have another agreement, interface requirement, the altitude control system, Roman ACS, to bring the star this time between 0.3 arc second of the center pixel. So the way that raster scan works is we use for fastering the raster the sky, and we have a photon. We count the photon count as a very fast rate of 1,000 hertz as a function of FSM strain gauge voltages. And each of the masks have its own pre-recorded voltage profiles. So we have trajectories that we have designed for each of these masks. Here we tested the HLC, of course, and each of these patterns are designed to scan across a specific mask for different feature sizes that we have. So again, the algorithm will start in the image, identify its location, offload that location to the ACS system, capture linear range. Because a successful raster scan will close the line of sight loop at the end. Autonomously, the flight software does that. So here again, we place the star at the 0.3 arc second radius. And this is a raster scan for HLC. And the raster image, it creates a raster image, and the algorithm finds the star and its location and load the location to the ACS, in this case CBS. So this is a HLC raster 0.48 or 0.48 per second. This is the strain gauge voltages for each mask. This would be different. And here we found the location of the star and then offloaded this to the ACS, in this case to CBS, to bring it to the lowest capture range. As you can see, here is where we can close the line of sight loop. The flux is recovered, and this is the low count image with expected morphology. And completion of the raster scan acquisition, we have closed the line of sight loop, and the FSM is centered, and we are offloading these strain gauge measurements to the spacecraft to keep the FSM centered, so we can keep the line of sight loop long. These are the requirements that we had, and we demonstrated that we can requirements. Of course, we use the bright stars, and we also turned the disturbances off when we were doing that. And all cases we showed that we can meet our requirements, and we closed the line of sight loop, which is very exciting. Okay, another thing that we tried during the acquisition was since we talked to the ACS, there are periods that ACS has to go through a reaction with zero crossing or moves the high gain antenna. Those are the times that the spacecraft ACS doesn't have the pointing stability that the CGI requires. So for those cases, we need to, the flight software needs to react to that. So we need to abort ongoing hands that are happening and protect the cameras, open the loops if they're closed. And after that event is done, spacecraft will send us the flags to say that they are stable enough that we can go on and continue our operations. So the flight software needs to go to active state, protect the cameras by turning them off or put them on idle mode and open all the loops. And then after we get the flag and put the flight software back the flight software puts them back to restores all the states prior to these states. So this was a complicated piece of flight software, and tested for many, many times and troubleshoot that. And finally, by TBAC, we had caught all the problems that we had with flight software and say that the flight software responds to ACF disturbances and recovers from them successfully. That was another requirement that we had. Okay, in summary, can say that all intended objectives for star acquisition, both the XCAM and master acquisition, was demonstrated successfully, met all the requirements. And again, I want to emphasize that the bi-weekly meeting that we had with the adjunct control system early on, that was really helpful in communicating our needs and before they finalize their design. They need what we need, and they accommodated that. Another thing is, okay, the acquisition algorithms that I tested, they were all for HLC mask, and we didn't have time for researchers to test the other masks thoroughly. So it's important to test acquisition algorithms for different masks before using them on orbit. Another thing that is that the system level star acquisition with ACS has never happened yet. So I think that would happen on orbit, and for any reason, for offloading, for any reason, if there are some directionality issues or phasing issues, we have some transformation matrices to indicate that. So hopefully be successful as it was during the TBAC process.
Right, thank you.
Sure.
There is one question online about what's this for crowded field. May have to do with our target selection. Can somebody read out the question online? Justin, I think that's a question from you. Are you going to speak your question?
Sure, yeah. I wanted to ask how well the algorithm works in if you have a more crowded field of stars. So if you have other stars within the 4 arc seconds of your target, or if your target is fainter in a more crowded field.
You want to
No,
pick up?
we have not. We are assuming that the star of interest is at least 30 arc seconds away from the crowded field.